Okay, welcome everyone once again. Let us look at chapter 8 notes now. So obviously this is MGTS 103 and what we will be looking at are chapter 8 notes. And as we have done in the previous videos, it would be best if you open your slides from Blackboard on in one window on your computer and then go through this video on in the other window. Okay, so before we get into this chapter, what I would like to, and of course what we will do in this chapter is we'll go through these four sections, um, and essentially let's just go back to this problem from chapter 7, question number 29, which says the CPA practice advisor reports that the mean preparation fee for 2017 federal income tax returns was $273. Use this price as a population mean and assume the population standard deviation, of preparation fees is $100. What is the probability that the mean price for a sample of 30 federal income tax returns is within $16 of the population mean? So what we were doing in that question was we said, let me just get my pen going here. Okay, so we said that this is the population mean, and then what is the probability that it is between 289 and so 273 and 257, right? And we were finding this area or probability. Okay, and the formula that we were using was we were first calculate the z-score by this formula, x bar minus mu divided by sigma divided by square root of n. Okay, now in this chapter what we're going to do is we will look at how do you estimate the population mean mu if it is unknown and we only know the sample mean. So essentially what we will do is we'll rearrange the formula from chapter 7. So let me write the formula once again. Z is equal to x bar minus mu over sigma divided by square root of n, or x bar minus mu is equal to z times sigma divided by square root of n, or so I'll take the mu the other side and the z sigma divided by square root of n on the other side. So it will be mu is equal to x bar minus z times sigma divided by square root of n. Okay, and then what we are just going to do is we will calculate, because remember x bar could be on the positive side and x bar could be on the negative side, right? So it could be here or it could be here. So we will say x bar plus minus z times sigma divided by square root of n, and we will have a small subscript here, alpha by 2, which I will explain to you. Essentially the area in the tails is going to be alpha by 2 and alpha by 2, and which means that this area in the middle is 1 minus twice alpha by 2 equals 1 minus alpha. Okay, so we will be given the alpha or the 1 minus alpha, and we will find the corresponding z value, and then everything else is given, and we will calculate this confidence interval. So this is called the confidence interval, and that is essentially what is chapter 8. Now what will happen in the later part of chapter 8 is that we will replace z by t, and I will tell you how that formula works, but it will be essentially a similar formula. Okay, so let us keep going and go through the slides. Now, let me just get my pen going. Okay, so now we know that in the previous chapters what we've been doing is we've been finding out a point estimator. So a point estimator is basically, for example, we want to know the population mean mu. So remember the old example where we said we want to find the average height of all students in a college, which is your mu, and let us say we found x bar, a sample mean based on a sample of size n equals to say 150. Okay, and we found it to be 5 feet, let's say 8 inches. Now the population mean mu may or may not be equal to 5 feet and 8 inches. So it may be equal to or it may not be equal to. So what happens is this 5 feet 8 inches, the sample mean is basically a point estimator, and it may actually give us the population mean or may not give a population mean. But if we were to, on the basis of the sample mean, if we were to say that the population mean or the mean height of all students at this college is 5 feet 8 inches plus and minus, let's say 6 inches, right? This seems to be a much more reasonable estimate of the population mean or the mean height of students at this college. So this 5 feet 8 inches we know is the sample mean x bar or the point estimate, and this 6 inches is our margin of error. This is the flexibility we are giving ourselves because we are only taking a sample size of 150 and we are not going to the entire population. So this entire thing, 5 feet 8 inches plus minus 6 inches, is called an interval estimate, and it tells us how close is a point estimate to the population parameter. So interval estimate is equal to point estimate plus minus the margin of error. So the point estimate for mean is x bar, and then the margin of error is what we will be calculating. And we will be looking at two cases, one where population standard deviation sigma is known. In that case we will be using this formula that I already showed you, and the formula will be mu, we'll be using this formula, mu equals x bar plus minus z alpha by 2. So alpha by 2 is not multiplied with z, it's a subscript, and I'll explain to you in a minute what that means, times sigma divided by square root of n. So we know x bar is the sample mean, we know the z is from the z-score, sigma is the population standard deviation, and n is the sample size. Now when sigma is unknown, the second case, we will use a similar formula. So mu is equal to x bar plus minus, now z will be replaced by t alpha by 2 times s divided by square root of n. Everything else is same as before. Now s is your sample standard deviation. Okay. Now if you do not know what is a t-distribution, please look up the other video where I've explained t-distribution and how to look up the t-tables. Okay, and we will be doing some examples in this video. Okay, so as we just said, if sigma is given to us, right, then we will use this formula, mu is equal to x bar plus minus z alpha by 2 times sigma divided by square root of n. X bar is the sample mean, 1 minus alpha is the confidence coefficient, and z alpha by 2 is the z value providing an area of alpha by 2 in the upper tail of the z table. Sigma is the population standard deviation, and n is your sample size. Okay, so what is this alpha and alpha by 2? Let me explain to you. So you know that when we have the standard normal distribution, so the mean value is 0, and let us say we have some kind of a z-score here, some positive z-score. So this area on the right hand side is alpha by 2. Okay, and so this z-score is called z alpha by 2. Now similarly, on the negative side, on the left hand tail, we will have minus z alpha by 2, and so this would be also alpha by 2, and so the area in the middle is going to be 1 minus alpha. Why? Because the total area is 1, so area in the middle is 1 minus twice alpha by 2 equals 1 minus alpha, which is known as the confidence coefficient. Now the three most common coefficients we use in business are 1 minus alpha equals 90% or 95% or 99%. in which case we will find the alphas, alpha by 2's, and then the z-scores. Okay, so we'll be doing some examples on that. Let's continue. All right, so this is, as I was explaining to you, this is a standard normal distribution and normal. So the middle value is the mean, population mean, and what we are going to find out is an interval such that we have alpha by 2 and alpha by 2 areas in the tails. Okay, and this is known as the sampling distribution of X bar, as we covered in chapter number 7. Okay, now as I was telling you, so the three most common values that we use for 1 minus alpha are 90%. So 1 minus alpha equals 90%, 95%, and 99%. So let us take a case of where 1 minus alpha is 99%. Okay, so let us say 1 minus alpha is 99%. So this is 0.99. Okay, so how much is this area? Well, this area is, remember, this area and this area together are equal to 1 minus 0.99, which is 0.01. That is the alpha right here. So alpha by 2 is going to be 0.01 divided by 2, which is 0.005. Okay, so this is going to be 0.005, and similarly this is going to be 0.005. Okay, now if you look up the probability tables such that the area on the right is 0.005, your z-score is going to be 2.576, and we call it as z alpha by 2. Now why is it 2.576? Because if you go to the z table right now, so if you go to the z table and look for an area of 0.005 in the body of the table, or an area of 0.9950 to the left of the table, right, or to the left of the curve. So basically what we are looking at in our probability table is this area is now 0.9950 because this area is 0.005. Okay, so if you look up that, you will not find this number, but what you would see is that 0.9950 is between two numbers. It is between 2.57 and 2.58. So it is between 2.57 and 2.58, and either you can, and this falls in the middle, so you could say it is 2.575, but the exact value happens to be 2.576, and this is a number that we'll be using so regularly that you will get to know this quite well. Similarly, when the middle area is 95%, then the z-score would be 1.960. We've done that before. And when the middle area is 90%, then the z-score comes to be 1.645. I do encourage you to go back to the probability tables for z-scores and make sure that you can find out these numbers such that you have these areas in the middle, and then this is the lookup area. Okay, if you have any questions, do let me know. Okay, so let's continue. Now let's go to a question here. So we are told that the sample size, we took a sample and the sample size is 36. Okay, and the sample mean income is 41,100, population standard deviation is 4,500, confidence coefficient is 0.95, estimate an interval that will include the population mean. So to think about the context for this question, think about that a survey was done in a city, and they want to find out the average income of people in the city, but obviously they can't go and talk to everyone, they can't do a census, so they do a sample of 36 people and find out the sample average. And what they want to know is what would be the population average or the average income in the city. So sigma is known, right? So let me just get my pen going here. So sigma is known, population standard deviation, so we will use the z formula. Okay, so what we would do is, sorry, okay, yeah, so we will use this formula. Mu is equal to x bar plus minus z alpha by 2 times sigma divided by square root of n. Now x bar, the sample average, is given to us as 41,100 in this question, and sigma, the population standard deviation, is given to us as 4,500, and the sample size is given to us as 36. Okay, now we are told that 1 minus alpha is 0.95, so this area is 0.95. So if 1 minus alpha is 0.95, alpha is equal to 1 minus 0.95 equals 0.05, and alpha by 2 is 0.05 divided by 2, which is equal to 0.025. So this area is 0.025. Okay, and then the lookup area is, all of this area is 0.975. 1 minus 0.025 is 0.975. So if you look up the probability tables, you will find that the z-score, or z alpha by 2 for this case, is 1 minus 1.96. Okay, so we've got all the numbers here now. So all we're going to do is we will use this formula and plug in the numbers. So mu is equal to 41,100 plus minus 1.96 times 4,500 divided by square root of 36. So if you solve this, you would get 41,100 plus minus 1470. Okay, so this is a sample average and this is your margin of error. So this is your margin of error, and if we add and subtract it, what we would do, we would get is, we would say mu is equal to 39,630 to 42,570. Okay, so 39,630 to 40,570, and this is, remember, 1 minus alpha, confidence coefficient is 0.95, so this is called the 95% confidence interval. 95% confidence interval. Some people, in kind of a layman language, they say that this is, we are 95% sure that the average income in this city is between 39,630 and 42,570, which is really neat because all we did was, amongst maybe the city has hundreds of thousands of people, but we only took a sample of 36 people, and we can say with 95% confidence that the average income in the city is between these numbers. So that is called an confidence interval, and you can go through the calculations once again on these slides as we just discussed. Okay, so there is a 95% probability that this interval contains the population mean. Okay, now yeah, remember I was telling you that if sigma is unknown, then we will use the T formula, which is which looks like pretty much like the Z formula, except that the Z is now replaced by T. And one thing you have to remember is that whenever we use the T, and I would like to remind you that there is a video that I've done on just looking up the T distribution table. Okay, so whenever we are calculating the T from that table, we always take n minus 1 degrees of freedom, where n is your sample size. Okay, and 1 minus alpha is the confidence coefficient as before, n is the sample size, and T alpha by 2 is the T value providing an area of alpha by 2 in the upper tail. So again, it's the same thing. This area is going to be alpha by 2, and this is the T score, or the T alpha by 2, with n minus 1 degrees of freedom. S is your sample standard deviation. Okay, so let's jump into a question here. Oh yeah, by the way, so what happens is that the T distribution, as for small sample sizes, is looks a little different from the Z table and the Z distribution and the normal distribution. But as we keep on increasing the sample size, the T distribution also starts looking very much like the Z table. Okay, so let's do this question. We have a sample size of 16. Sample mean is $7.50. Sample standard deviation is $55. Confidence level is 95%. Estimate the interval for population mean. So let's think about a context for this question. Say we are trying to find the average rent of studio apartments in downtown core of a city where a university is located, and international students would like to know what kind of monthly rents can they expect. So you did a project for the university and you took a sample size of 16, and you said, well, based on my sample size, the average in my sample was $750 is the monthly rent, and then we want to find out what would be the monthly rent of all the apartments, or the average monthly rent of all the apartments in this downtown area. Okay, so since we are given sample standard deviation S, we will use T with n minus 1 degrees of freedom, which is in this case 16 minus 1 is 15 degrees of freedom. Okay, and then 1 minus alpha is 0.95 or 95%. So alpha is 1 minus 0.95 equals 0.05. Alpha by 2 is 0.025. Okay, so let me just go to the next table, the T table, just to remind you how to look up the T tables. So the degrees of freedom are on the left hand side right here. It says degrees of freedom, and then on the top you have the probabilities or the areas in the upper tail. So for 15 degrees of freedom and 0.025 is alpha by 2, the T score is 2.131. Okay, so that's the T score. So let's go back. So our T score is, or T alpha by 2 is 2.131. Okay, so then we will be using this formula. Mu is equal to x bar plus minus T alpha by 2 in the subscript times sig S divided by square root of n. X bar is $750. S, sample standard deviation, is 55, and the sample size is 16, and the T score we just calculated is 2.131. So we just plug in the numbers. So mu is equal to 750 plus minus 2.131 times 55 divided by square root of 16. So let me just bring the answers here. So mu is going to be equal to 750 plus minus 29.30. So this 29.30 is again the margin of error. Margin of error. Okay, and so we could say that the average rent in the downtown core is mu is equal to so if I subtract 29.30 from 750, that will come to $720.70. So mu is equal to $720.70. If I add 750 with 29.30, that comes to 779. So $779.30. Okay, and so this is called the 95% confidence interval because that's the confidence level that we used. Okay, so if you go through the slides, you will see the same calculations here, but now it's probably easier to understand. Okay. Okay, so in summary, what we are supposed to do is you're going to ask yourself in a question, is the population standard deviation sigma known? If it is known, we use the Z formula. And if it is unknown, if we use the sample standard deviation and we use the T formula. Okay, the formulas look the same except that Z is replaced by T and sigma, the population standard deviation sigma, is replaced by the sample standard deviation S. Okay, now suppose that we are doing a project and we do not know the sample size. How much should be our sample size? So based on the confidence level that we want and the desired margin of error, we can also calculate the sample size. So let E be the desired margin of error. So E is the amount added to or subtracted from point estimate to obtain an interval estimate. And if we select the margin of error before the sampling, we can find out the necessary sampling size. So how do we do that? Like this. So we know that mu, let me just get my pen going here. Yeah. So mu is equal to x bar plus minus z alpha by 2 times sigma divided by square root of n, or x bar plus minus e, the margin of error, right? Where e, margin of error, is equal to z alpha by 2 times sigma divided by square root of n. Okay. Okay, so if E, the margin of error, is known, we can rearrange the terms and we can say sigma square root of n is equal to z alpha by 2 times sigma divided by E, or n, the sample size, is equal to z alpha by 2 times sigma divided by E and square of all of that. And so that is your sample size once E, the margin of error, is known. So that's the formula here, the one that we just looked at. Okay. Now, if you go back to the formula, you can see that the sample size formula also requires us to know the population standard deviation. But if we have not done any sampling, then how would we know sigma? We probably do not know sigma. So if sigma is unknown, we can use some kind of a preliminary value. And what we can do is we can either use an estimate from a previous study or use some kind of a pilot study to estimate sigma, or in many cases we can just use judgment for sigma, where we say sigma is equal to maximum minus minimum. Remember, that is the range divided by 4. So we can just use this formula if sigma is not given to us at all. Okay, so let's do a question. Population standard deviation sigma is 4500 and 0.95 probability that the sampling error, so remember, sampling error and margin of error are the same things, so they mean the same. Sampling error is $500 or less, sampling error. How large a sample size is needed to meet the required precision? So say, for example, again the same thing, you're trying to do a study, you want to find out the sample size, how big your sample size should be, and you know that the standard deviation in incomes for this city is 4,500, and you want your margin of error to be 500 or less. So remember our formula was n equals z alpha by 2 times sigma divided by E square. Okay, so 1 minus alpha is 0.95. So alpha is 1 minus 0.95 is 0.05. Alpha by 2 is 0.025. So if this is alpha by 2 equals 0.025 and we look up the z table, we will find that the z-score is 1.96. Okay, sigma in this question is given to us as 4500, and E, the margin of error or sampling error, is given to us as 500. So all we need to do is to plug in these numbers. So n is equal to 1.96 times 4500 divided by 500 square. So that comes to 311.17, and we take a conservative estimate. So 312 is our sample size. So the estimated sample size is 312, and this is what is done on this slide. So you can go through the calculations here. Okay, now just as we did proportions in chapter 7, and we were trying to estimate the point estimate for proportions in the form of sample proportion, we can do the same thing. We can find out the interval estimate for population proportion. So we can say P is equal to P bar plus minus margin of error E, where E, the margin of error, is going to be equal to Z alpha by 2 times P1 minus P divided by N. So P bar 1 minus P bar divided by N. P bar is the sample proportion that will be given to us, and N is your sample size. And we can use this formula whenever N times P is more than equal to 5 and N times 1 minus P is more than equal to 5. I would say P bar and P bar, right? And where N is your sample size. Okay, so, and to give you a context for this question, so if you go back to question 39 from chapter 7, they said in 2016, the Better Business Bureau settled 80% of the complaints they received in the US. Suppose you've been hired by the Better Business Bureau to investigate the complaints they received this year involving new car dealers. You plan to select a sample of new car dealer complaints to estimate the proportion of complaints the Better Business Bureau is able to settle. Assume the population proportion of complaints settled for new car dealers is 0.8, the same as the overall proportion of complaints settled in 2016. And B is based on a sample of 200 complaints, what is the probability that the sample proportion will be within 0.04? So in this question, what we know is that the sample proportion is what we have to find, but this 0.04 is our margin of error. Okay, so that is given to us, and we were to find the probability. Okay, but now in chapter 8, the probability is given to us, and what we have to find is the margin of error. Okay, and as I said, we can use the normal distribution formulas, or the formulas that we've been using for proportion, whenever n times p is more than equal to 5 and n times 1 minus p is more than equal to 5, which basically says that we should have a large enough sample size, which is usually the case. And again, what we would have is we will have the sampling distribution of p bar, which looks like a normal distribution. The middle value is the mean, and then we are going to find out an interval estimate, okay, such that the area in the tails is alpha by 2. So as I said, the formula that we are going to use is P is equal to, so the population proportion P is equal to sample proportion P bar plus minus Z alpha by 2 times square root of P bar times 1 minus P bar divided by N. N is your sample size, P bar is your sample proportion, and then 1 minus alpha is the confidence coefficient, just as before. Okay, so let's jump into a question here. Let's say an election is going to happen and you are doing a survey before the elections to see who's likely to win, and let us say you did your survey with 500 people. That was your sample size, and out of 500 people, 220 favor candidate Smith, and you are to develop a 95% confidence interval estimate for the proportion of voters that would favor candidate Smith. So first of all, let's see N times P. So that is 500 times, so what is P here, or P bar? The sample proportion is candidates, people who favor Smith divided by total number of people. So 220 divided by 500 is 0.44. Okay, so 500 times 0.44 is equal to 200, and of course 220, which is more than 5. Similarly, N times 1 minus P is equal to 500 times 1 minus 0.44, which is equal to 280. This is also more than 5, so which basically means that we can use this formula. So P equals P bar plus minus Z alpha by 2 times P bar 1 minus P bar divided by N. Now P bar is known to us, 0.44. We need to find the Z score. N is known to us, sample size is 500. So how do we find Z alpha by 2? Well, we know that 1 minus alpha is 95% or 0.95. So alpha is 1 minus 0.95 equals 0.05. Alpha by 2 is 0.05 divided by 2 is 0.025. So if we have the standard normal distribution such that this area is 0.025 and we look up the Z table, the Z score will be 1.96. Okay, so we've got all the numbers, so let's plug in here. So P is equal to 0.44 plus minus 1.96 times 0.44 times 1 minus 0.44 divided by 500. Okay, so that comes to 0.44 plus minus 0.035. So this 0.035 is the margin of error. So these are the people who, this is the 95% confidence interval of proportion of people who would be voting for candidate Smith. Okay, so that if we subtract and add, so this should come to 0.3965 to 0.4835. Okay, so out of the total number of voters in this area, we expect that we can say with 95% confidence that the proportion of people who will be voting for candidate Smith is ranges from 0.3965 or 39.65% to 48.35%, right? And that we are saying on the basis of a sample of 500 voters. So that's pretty neat, right? So you can go to this slide, the next one, and here the calculations are done. The same calculations. Okay, now just as we calculated the sample size for the average, the sample average and the population average, we can use the same, we can also calculate the sample size for proportions. So similarly, remember E, the margin of error is equal to z alpha by 2 times square root of p bar times 1 minus p bar divided by n. If you rearrange the terms, so n comes here, okay, so n comes here and e goes here, you will see that the n is equal to z alpha by 2 square times p bar 1 minus p bar divided by e square. So that's the formula for sample size. Now P bar will not be known. This is the sample proportion until we have found the sample, right? So what we do is we will use some kind of a planning value P star for P bar. So what we'll say is that the sample size is Z alpha by 2 square times P star 1 minus P star divided by your margin of error E square. Okay, now if we do not know P star, what we should do is we just take it as 0.50 or 50%. Kind of sounds reasonable. We are saying that 50% of the people is the proportion that kind of favors or is our sample proportion to start with, right? So that's so if the planning value P star is not given to us or is not available, then we can find it from a previous study or a pilot study, or just use it as 0.50. Okay, so let's do a question. So again, going back to the same question, out of 500 voters, 220 favor candidate Smith. We want our 0.99 probability that sample proportion is within 0.03. So 0.03 is your margin of error of population proportion. How large a sample size is needed? Now note that 200, so P bar is 220 divided by 500 is 0.44. 1 minus alpha is 0.99. So alpha is 1 minus 0.99 is equal to 0.01. So alpha by 2 is 0.01 divided by 2 equals 0.005. So the z-score such that, again, we have this area as 0.005. Okay, the z-score is going to be 2.576. So the z-score is 2.576. Okay, so and then the margin of error E is given to us as 0.03. So let's just plug in the numbers in this formula. The formula is n is equal to z alpha by 2 square p star 1 minus or p bar 1 minus p bar divided by e square. So this is equal to 2.576 square times 0.44 times 0.56. 1 minus 0.44 is 0.56 divided by 0.03 square, which comes to 1817. So we would need a sample of size 1817 if we want to be within 0.03 of the population average proportion. Okay, so if you go to the calculations on the next slide, a sample of size 1817 is needed to reach a precision of 0.03 at 99% confidence. Okay, now note that in the previous question we used P as 0.44, but let's say the P is not given to us, and instead of that we used P as 0.5 or 50%, right? So if we were to use this, so n equals z alpha by 2 square times P star 1 minus P star divided by E square. So this is equal to 2.576 square, right, times 0.5 times 0.5, right? 0.5 times 1 minus 0.5 is also 0.5 divided by 0.03 square. If you solve this, you will get 1843, right? So even if the proportion is not given to us, we can just use a planning value of half or 0.5, and that would have given us a slightly higher required sample size of 1843. Okay, so with that, we finished the chapter. And there are some questions that I would like to now solve. Remember that in the other video, I've already solved question number 11 and 12. So I'm not going to do them again. I'm going to look at question number 3, 10, 19, 27, 32, and 33. And then I would suggest that you do some of the other questions that I've listed at the end of the slides. Okay, so so these are the questions that I would like you to do at home. And as I've said, that their answers are already in the book, in the ebook, and I've also posted them on Blackboard. Okay, so let's go to question number 3. Okay, let me get my pen going. A simple random sample of 60 items resulted in a sample mean of 80. So n is equal to 60 and sample mean x bar is equal to 80. The population standard deviation is sigma equals to 15. So sigma is given to us, so we are going to use the z formula. So use z. Compute the 95% confidence interval for the population mean. So we know that 1 minus alpha is given to us as 0.95. So alpha is 1 minus 0.95 is equal to 0.05. Alpha by 2 is 0.025. So if this area is 0.025, then the z-score is going to be 1.96. Okay, so compute the 95% confidence interval. So we know that the formula for confidence interval is mu is equal to x bar plus minus z alpha by 2 times sigma divided by square root of n. So x bar sample mean is given to us as 80 and plus minus sigma z is 1.96. Sigma is 15 and sample size is 80. So this comes to 80 plus minus 3.8 or 76.2 to 83.8. So that is your 95% confidence interval. Okay. Part B, assume that the sample mean was obtained from a sample of 120 items. So now in part B, the only thing that has changed is the sample size. Now sample size has gone up to 120. So let's see what happens to the margin of error and to the interval estimate. So now again, we'll use the same formula. Mu is equal to 80, the sample mean, plus minus 1.96 times sigma is 15 but divided by square root of 120. So this comes to 80 plus minus 2.68 or 77.32 to 82.68. So part C says, what is the effect of a larger sample size? Well, when n, the sample size, goes up, your margin of error E, if you can see, it goes down from 3.8 to 2.68. So the margin of error goes down and your interval estimate or your interval becomes narrower, which is good, right? So everything is good. So as you increase the sample size, margin of error E goes down and interval becomes narrower. Okay, so let's go to question number 10. Costs are rising for all kinds of medical care. The mean monthly rent for at assisted living facilities was reported to have increased 17% over the last 5 years to $3,486. Assume this cost estimate is based on a sample of 120 facilities, so that's your N. And from past studies, it can be assumed that the population division sigma is $650. So part A is develop a 90% confidence interval estimate of the population mean B is develop a 95% confidence interval of the population mean. Part C is develop a 99% confidence interval estimate of the population mean. And D is what happens to the width of the confidence interval as the confidence level is increased. Okay, so as you know that the answers to this question are already given in the solution set. So what I'm going to do is I'm going to do part A. Okay, so this is what I'm going to do now, and then I would suggest that you do part B and C on your own and compare your answers with the answers that I'm going to give you, and we'll see what is the effect of increasing the confidence interval on the width of the interval. Okay, so in this question sigma is given, so we will use the Z formula. Okay, now what we are told is that so I'm doing part A now, part A. So in part A, 90% confidence interval means 1 minus alpha is 0.90. So alpha is 1 minus 0.90 equals 0.10. Alpha by 2 is 0.05. So if this area is 0.05, the z-score is going to be 1.645. Okay, and we'll be using this formula where mu is equal to x bar plus minus z alpha by 2 times sigma divided by square root of n. So x bar is $3486. Z we just found to be 1.645. Sigma, the population standard deviation, was $650, and n, your sample size, is 120. So mu is equal to 3486 plus minus 1.645 times 650 divided by square root of 120. So if you solve this, you get 3486 plus minus 98, or 34 sorry or dollars 3388 to dollars 3584. Okay, so this is your 90% confidence interval. 90% confidence interval. Okay, now in part B, where the confidence interval goes up to 95%, you will find that your answer comes to mu is equal to 3486 plus minus 116, or 3370 to 3602. Because what's going to happen is that when we increase the confidence level to 95%, the z-score is going to change, and that will change your margin of error. So, and then in part C, at 99% confidence interval or confidence level, mu is going to be 3486 plus minus 153, or 3333 to 3639. So that's the 99% confidence interval. So what is happening as we increase confidence level, right? In other words, as we decrease alpha, margin of error E goes up and confidence interval becomes wider. And why is that the case? Because what is happening is, if you think about it, it makes intuitive sense, because we want to be more and more sure. So if you want to be more and more sure, then we need to give ourselves more and more flexibility in terms of the margin of error, and so our confidence interval becomes wider. So this is a very important result, and often people kind of get mistaken here, because they think that if you're increasing the confidence level, then we should be actually getting a better estimate. But what's happening is, as we are increasing the confidence level, our margin of error is increasing for the same sample size if we don't change the sample size, and the confidence interval becomes wider. Okay, so as I said, I've already done question number 11 and question 12 in my other video on how to look up the t-table. So let's go to question number 48. Oh, sorry, question number 19 on slide 48. The mean cost of a meal for two in a mid-range restaurant in Tokyo is $40. How do prices for comparable meals in Hong Kong compare? The data file Hong Kong meals contains the cost for a sample of 42 recent meals for two in Hong Kong mid-range restaurants. So if you look at Blackboard under chapter 8 notes, you would see an Excel file that includes data on these 42 restaurants in Hong Kong. Part A is with 95% confidence, what is the margin of error? Okay, now in this question, the population standard deviation sigma is not known. So sigma is unknown. On the other hand, if you look up the Excel file, we have prices of 42 restaurants in Hong Kong. So based on those 42 prices, what we can do is we can find out the sample average X bar, which would come to 32.66. So have a look at that Excel file and see if you can calculate the average, which would come to 32.66. And also remember chapter 3, where once we have some data values, we can calculate the sample standard deviation S, right, by this formula, X minus X bar square sigma divided by n minus 1 square root. Okay, so that's a sample standard deviation. And you can also do these calculations in Excel, or you can do by hand. Well, for 42, that will be too much to do by hand. But if you have a smaller sample size, you could probably do it by hand. But Excel does it for you. So if you calculate the samples, so remember this is a sample standard deviation. So if you use the sample standard deviation formula in Excel, you will find that S comes to 6.827. So that's the sample standard deviation, and then the mean is 32.66 for Hong Kong. Okay, because the sigma is unknown, we will use t distribution with n-1 degrees of freedom. So because we have data on 42 restaurants, so n-1 is going to be 41. So 41 degrees of freedom. So now if you look at 95% confidence level, which means 1 minus alpha is 0.95, which means that alpha is 1 minus 0.95 equals 0.05, and then alpha by 2 is 0.025. So alpha by 2 is 0.025, and we have 41 degrees of freedom. So if you look up the t value or the t table, you will find that the t value comes to 2.02, okay, such that the probability in the right tail is 0.025, or the area, and 41 degrees of freedom. Okay, so what we've got all the numbers here. So let's do our calculations. So we will be using this formula. Mu is equal to X bar plus minus T alpha by 2 times S divided by square root of N, where X bar is 32.66. S, the sample standard deviation, is 6.827. T value that we just found out is 2.02, and N, the sample size, is 42. Okay, so let's just plug in the numbers. So mu is equal to 32.66 plus minus 2.02 times 6.827 divided by square root of 42. So this comes to 32.66 plus minus 2.13, where 2.13 is your margin of error E. So this is part A. Part B is then mu is equal to, if we just add and subtract, comes to dollars 30.53 to dollars 34.79, and this is our 95% confidence interval. So this is your, oops, sorry. So this is your 95% confidence interval for Hong Kong. So meal for two in Hong Kong, average price of a meal for two in Hong Kong. Now in part C is how do these prices compare? Remember, in Tokyo, the average is dollars 40, and in Hong Kong, the average is 30.53 to 34.79. So it does seem, if you compare the two, that Hong Kong is cheaper than Tokyo if you're going out to eat. Okay,